Today, my presentation is on best practices with radiochromic film. I'm Maria from Memorial Sloan at Basking Ridge. I would like to acknowledge that I have a research grant from Ashland, the manufacturer of radiochromic film. First, I will talk about where we are in radiochromic film dosimetry. Next, I will introduce various types of radiochromic film and best practices for the film. Then I will talk about recent advancements in radiochromic film dosimetry, including multi-channel dosimetry, one-scan dosimetry protocol, and then give you some clinical samples of the applications. Before I start, I would like to show you what equipment and tools I have used. 3 variant Linux, a Gamma Mac, HDR, and Memorial Sloan in-house treatment planning system, Equip and iPlan treatment planning systems, Radiochromic EBT3 film QA Pro, and Epson 10,000 XL scanner, and a Radiochromic Quick Phantom. If you don't have such a Phantom, you just need 2 slabs of 5 cm thick solid water. There was an APM task group 55 on radiochromic film formed about 20 years ago, and the task group report was published in 1998. Since then, there has been many changes and advancements. Therefore, a new task group was formed to update task group 55. The charges of the task group are to review the literature on the radiochromic film dosimetry and to evaluate scanners for digitizing radiochromic film, to outline the procedures for accurate dosimetry, and to evaluate measurement uncertainties, then to provide guidelines for clinical uses. Today, my talk is mostly on my own personal experience and does not include any official recommendation from the task group. To report on how the radiochromic formulation described in task group 55 are being used in practice. B, describe which dosimetry tests are acceptable for implementation of task group 142. To update task group 55 and report on the performance of the current generation of radiochromic film. D, to require the use of radiochromic film for all clinical measurements. E, to replace 2D detector arrays with radiochromic film. That's correct. The correct answer is to upgrade task group 55 and report on the performance of the new generation of radiochromic film. As you all probably know already, radiochromic film is self-developing. Since it changes colors on exposure to ionization radiation, it can be handled in room light, be cut to size, bent to shape, and can be immersed in water. The EBT3 film has a wide dynamic range from 2 centigrade to 4,000 centigrade. The spatial resolution can be up to 1,000 dpi. With the new software and protocol, the film dosimetry has become more accurate and user-friendly. There are many different types of film for different purposes. For example, for beam positioning, here are the choices. If you want to do a Linux or HDR QA, you would pick RTQA2 for radiology application. XRQA2 1 or 2 has the highest low energy response. So it is for diagnostic X-ray QA. The XRCT2 is for CT, XRM2 is for mammography unit QA. All these types are for the positions or localization of the beam, not for those QA. Here are the types for those measurements. For radiotherapies, EBT2, EBT3 are very commonly used and are the successor of the EBT film. The EBT2, EBT3 is about 10 times less sensitive to the ambient light as compared to the EBT film. For radiology, those assessment, XRV3 film has immediate visualization of patient exposure, and with the software, the magnitude, location, and detailed dose distribution can be obtained.
When you're reset,
yeah.
Once it finishes the counter, you need to read the question and the possible answers.
Okay.
I'm resetting it.
Okay. And here's another question. Which of the following statement on the radiochromic film is true? RTQA2 is for MRT dose QA. EBT23 is more sensitive to light than EBT film. XRV3 has the highest low energy response. XRQA2 has the highest low energy response. And EBT-XD film cover a dose range up to 10 grade. The D is the correct answer. As I said earlier, the XRQA2 has the highest low energy response. Now let's go over how to handle radiochromic film. In order to optimize the useful life of the film, it is suggested to store the film in the dark at the temperature under 25 degrees Celsius, and average humidity less than 50%. Try to avoid dust, fingerprints, or crimping. For film scanning, a medical-grade film digitizer, such as VIDAS, or document types flatbed scanner, such as Epson, should be used. Besides being much less expensive, the flatbed scanner would have an option for multi-channel dosimetry because of its 48-bit RGB color. However, there's lots of rules for using flatbed scanner to achieve accurate dosimetry. For example, placing a piece of glass on pressing the film flat, and keeping the same orientations and location on the scanner for both calibration and the QA film. No matter what scanner type is used, you also need to consider temperature and moisture change, and the post-exposure film density change between the calibration and the dose QA. Since I'm going to talk about multi-channel dosimetry today, the flatbed scanner is the only choice here. Here it shows how you set up the Epson scanner. First, the scanner must have a transparency adapter. Use professional mode. Let's see. And choose film and 48-bit color for multi-channel dosimetry. And click on the configurations and turn off the color correction, so all the icons are grayed out. When you scan, either landscape or portrait direction is usable, but has to be consistent for all films. I prefer use portrait orientation, which is the scanning direction going through the longer side of the film. There are some angular dependencies during scanning. It is about 0.15% per degree, so try to keep the film oriented properly. There are non-lateral response artifacts for flatbed scanner. So try to place the film in the center of the scanner in portrait direction. If you scan the film in an extremely lateral position, the artifact will be larger in a single channel dosimetry than in a triple channel dosimetry. Also, you should be aware of the post-exposure density growth of the exposed film. For best results, ideally, you should wait at least 24 hours to read the film, because waiting for 24 hours corresponds to a dose error less than 0.5%. Now it's time for another questions. For quantitative dosimetry, radiochromic film A does not require any special care when using. B can be placed on a scanner in any orientation and then used in any orientation. C does not require a separate calibration for determining the dosimetry response. D must be handled consistently with respect to storage, temperature, irradiation, and scanning. E must be kept at the same size as supplies from the manufacturer. Yep, got it. The correct answer is D. Now I'm going to talk about some recent developments in film dosimetry. We have been using single red channel dosimetry for many years. Now we are moving toward multi-channel film dosimetry, which removes local disturbances in film dosimetry and achieve a better calibration function. I will give you more detail later. Also, one-scan dosimetry protocol can eliminate inter-scan variations, environmental effects such as temperature and humidity, and even correct for post-exposure density growth so that you don't have to wait for hours. So what is multi-channel film dosimetry? Use of all three color channels allows for the separation of the scan signal into one part that is dose dependent, C sub D, and another part is the dose independence, delta C. This enables the correction for disturbances in the digitized image, including non-uniformities in the film, as well as the scanner-related artifacts. Thus, the triple channel method increases the signal to noise level, mitigates the lateral artifacts, and extends the usable dose range to 100 gray. For example, the single red channel dose range usually is up to 10 gray, versus triple channels 100 gray. The multi-channel method can optimize the calibration and correlate calibration parameters for best consistency. Therefore, one can significantly improve dose map accuracy. For example, 1% is achievable in a triple channel versus 3% in a single channel method. On the left side is shown the third to fourth order polynomial fitting, which is typically used for red channel dosimetry. The single channel is simple and easy to correlate. However, as you see, for the higher dose range, such as more than 10 gray, it is not consistent with the fundamental property of the film. However, triple channel method use rational function fitting, which is consistent with the behavior of the film and easily inverted. This is a screenshot of the Film QA Pro software that shows how I perform the calibration using triple channel dosimetry. First, I scan all calibration films into different dose groups. The dose shown here is represent the maximum dose of the group. For each group, you only need 4 to 7 doses, including the background, the 0 dose. Usually, 4 calibration films are enough for clinical dosimetry. But make sure the spacing of the doses follow the pattern, such as the top, let's say 1200 centigrade, the next dose level will be 600, and then 300 and 150. And don't forget the 0. Now, time for another question. When multi-channel dosimetry is used instead of single channel, which of the following must be true? A is non-uniformity correction is the same. Curve fitting for the dose versus response is not needed. C, a third to fourth order of polynomial fit must be used for the calibration data. D, better corrections can be made for anomalies, artifacts, and other disturbances. E, any type of film digitizer or scanner can be used for high quality result. D is correct. So the C, the polynomial fitting typically used for single channel dosimetry. And you can find a reference in this paper published in Medical Physics Journal. Now I'm going to talk about one-scan film dosimetry protocol. The one-scan protocol means to scan the patients and the reference film together. In other words, when you do your QA measurement, all you need is to expose an additional film to a known dose, because the other is the background. So the top one is background, the other is another known dose additional to the QA film. And then one can rebuild the calibration curve with a 2-point rescaling. This protocol compensates any scan-to-scan variations, ambient conditions such as temperature and humidity change, and mitigates energy dependence. However, this protocol does not compensate for local disturbances, film non-uniformity, curl, Newton rings patterns, noise, lateral scanner effects, and of course, any calibration errors. So there's an ability to, another benefit of the protocol is dealing with the post-exposure change. So there's an ability to obtain dosimetry in minutes, not hours. Here's the explanation. As I said earlier, for absolute aging, when waiting 24 hours, the dose difference is less than 0.5%. But for one scan protocol, the relative aging of the film can be accounted for by just waiting 4 times of the duration between the irradiation of the reference dose film and the QA film. So the dose difference could be less than 0.5%. These slides show you the one scan method. The first step, the master calibration curve. You could have different master calibration curve in different dose ranges. Next, one scan digitization, the reference dose should be about 90% of the maximum dose of the QA film, and then wait 4 times of the duration between the irradiation of the reference dose film and the patient's film, and then get the overlaid isodoses for gamma analysis or dose difference map. Here is the example, an RMRT film along with the reference film with the 300 centigrade were exposed and scanned on, let's say, February 17 last year. And I used the same calibration data done on December the year before, and the result is the same as if I did the full calibration and RMRT QA on the same day. If you get used to your in-house software, or your software has certain features that the Film QA Pro does not have for film analysis, you can always export the dose map with a scaling factor of the maximum dose divided by 65,536. And this way, you could still have the multi-channel dose map with your own software, but to display one color at a time. This shows you the workflow for film dosimetry. Deliver one fraction of dose to the phantom and one reference dose, and then wait for 4 times of the duration to scan. What I mean 4 times is, let's say you scan the known dose now and the IMRT film 5 minutes later. So 4 times 5, that means 20 minutes you can read, you can get the readout. Now I will show you some clinical examples of film applications such as treatment machines and the planning system commissioning. Here are some LINAC QA films and an XDR source positioning verification film. And for research, you can even measure a surface dose profile at a very shallow depth, such as less than 2 millimeter depth. Shown here is the star shot for machine any QA. In this case, the radius of the outer circle is 0.6 millimeter, analyzed by the software. And here is the analysis of the weekly dynamic MLC QA, the picket fan test. So here is our extremely difficult 3-dose level painting VMAC case in Eclipse. Delivery is 6th grade to less than 6th grade to the hippocampus, and the 32 grade to the whole brain, and 63 grade to 3 lesions concurrently. In Eclipse, just create a verification plan using a phantom, either the quick check phantom or just 2 pieces of 5 cm water equivalent plastic. Here is the gamma analysis, 97% pass rate for 2%, 2 millimeter. You can also perform patient QA with different prescribed doses on the same day with only one known dose reference. Do you remember I showed you either earlier, I have many different dose curve for patients. So I can easily, based on the prescribed patient dose, I can choose the correct, appropriate calibration curve to do the analysis. And so here is an analysis of one SBRT lung Vmax, 99% passing rate for 2 millimeter, 2%, and the curve in the middle is the gamma passing rate as a function of gamma index. Shown here is the film application in small field dosimetry, such as for iPlan commissioning. One can continue the iPlan MLC model, such as 1 by 1 MLC or 2 by 2 cm MLC profile. And the dose can be exported from the triple channel and displayed in our in-house software display. This is a red channel display. Next, I move to the brachytherapy dosimetry. This work was done using multi-channel dosimetry, but with a different multi-channel method developed in MD Anderson Cancer Center. Shown here is the dosimetry of an eye applicator using strontium-90. Here is another example using the one-scan protocol for brachytherapy sources. Remember, the reference dose can be from a 6 MV LINAC because EBT3 film is nearly energy independent in the therapeutic dose range. As you can see, the scan direction is always along the long side of the scanner, and the region of interest should be located in the central area of the scanning window. This shows the lateral response artifacts for both dosimetry methods. This is important because the QA film is positioned toward the right side of the scanning window. So the triple channel method gives a better result than the single channel method. This is from another example of the commissioning of HDR sources with iridium 192 and a cobalt 60 done in the UK. This is a brachytherapy planning system commissioning from the same physicists in the UK using multi-channel one-scan protocol. My last topic is the in vivo dosimetry. Patient skin dose measurement, especially the bolus effect from the patient supporting devices, such as alpha cradle, IGRT couch, and etc. This is an in vivo skin dose measurement. So on the top is a SBRT treatment lung. And the figures on the bottom are the in vitro measurement in phantom with and without alpha cradle and IGRT couch. As you can see, the dose is quite different. Usually in our treatment plan, I know in the past, we not really include all the alpha cradle or IGRT couch in the calculation. Now, these days, there's more and more included with the availability in the treatment planning system. This is a one-scan protocol for a patient skin dose verification. Since it's a single electron covered a large extensive area of the scalp, so I placed 5 different pre-cut EPT3 films on the patient's scalp, and the prescribed dose is 300 centigrade prescribed to 90% using 6 MeV electrons. Right after the patient treatment, I immediately expose a reference film to 270 centigrade. Since the maximum dose I expect on the patient's skin under 1 cm bolus would be more than 300 centigrade, so 90% of the maximum, so it's 270. And then I pick the calibration curve. The maximum dose of the calibration is 450 centigrade for analysis. And the top, you can see the 5 readings from the Film QA Pro. The readout was performed about 20 minutes after the patient's treatment. I promise this is the last question for my talk. The one-scan protocol is able to eliminate which sources of dose error: A, inter-scan variation and temperature and humidity effects; B, differences between using different film lots; C, the amount of time it takes to get good dosimetry data; D, only differences between the different types of scanners; E, only temperature effects. Yeah, A is correct. Even though there's the one scan protocol can save lots of time. I think, well, I hope you found the subject to be helpful. Thank you for your attention. Okay.